Thank you very much for inviting me, and welcome everybody. Thanks for joining us. So for those of you who don't know me, my name is Simon Brown, and I'm an independent consultant specializing in software architecture. And one of the things I have been particularly interested in over the past decade or so is visualizing software architecture, because it's not something that is done particularly well these days. So of course, back in 2001, the Agile Manifesto was created. And over the past decade, or really 2 decades, I guess, many teams have thrown away big design up front. Now that's a good thing, because big design up front is very wasteful, it's very speculative, and of course, we all know the problems with that. Unfortunately, many people also threw away architectural thinking, documentation, diagramming, modeling, and all of these things when they ditched big design up front, because they thought that they're not part of an agile way of working. And that's not the case, of course. So it was interesting at the end of the last talk, you mentioned about architecture charters. So I've been flying around the world, pre-pandemic, of course. I've been flying around the world and running architecture charters for organizations. And really, this is in attempt to do 2 things. Number one, to teach people about hands-on, lightweight, developer-focused software architecture, and to practice design skills and collaboration and that sort of thing. And number 2, it's really to get people practicing how to communicate their solutions and software architectures through diagrams. So I've seen hundreds and hundreds and probably thousands of diagrams over the past few years, and they've all been mostly terrible. So here are some examples of diagrams I've seen in the past. What we do, just backtrack a second, we give the attendees of my workshops and requirements, we break them into groups. We say, you have an hour and a half, go do some design, draw some pictures. So these are the types of pictures that end up coming out of the workshops during the first iteration. This one here is a set of technology choices in a diagram. It doesn't tell you much more than that. This one here is like boxes and no lines. There's an ASP.NET box that stopped doing something, although it's not labeled. A bunch of SQL Server things at the bottom, I'm guessing representing databases, but there could be tables, views, who knows. And the things in the middle are like the decomposition of the solution into modules or components or services or subsystems. Again, I'm not really quite sure, because that's not explicit here. And there's nothing linking these things together. One of the ways I like to talk about software architecture and define software architecture is that it's about structure. Part of the definition is about structure, and that's really talking about building blocks and links to other building blocks. So this diagram is only telling you half the story. This is also super common. It's called a functional view, and again, it's just a list of things that this group decided that they need to build. We've got a different color coding as well, and I've no idea what the color coding means. It could mean anything. This one here, one of my all-time favorites, is the airline routes map. The little green circle in the top right points to everything that's important. It's like London Heathrow or something. And the rest of it's just a complete mess of different colors, shapes, line styles, and so on. This one here is often called the high-level logical architecture or the conceptual architecture. And again, it's just a list of things that need to be built, but it doesn't tell you much more than that. It's missing all sorts of things about the solution. I also love these diagrams because they have security in a box, and of course it's important to have security in our systems, but this doesn't tell you anything about how we can actually implement security, which is unfortunate. This one here is like an adventure game. Start at the top, go down through the picture, get to follow different paths, fail, complete, reject. It's all one color, it's very cluttered. It's showing a more complicated, event-driven, asynchronous style of architecture, funny symbols, acronyms, etc. This one here has people. I like people on diagrams because having people on diagrams allows us to provide some context as to how the software systems we are building fit into the world around us. But I want to know who these people are and what they're doing. Otherwise, they're just faceless, anonymous clones like stormtroopers here attacking this poor reporting service. Whiteboards. Pre-pandemic, of course, whiteboards are super, super useful because you can write some ideas up, erase it, iterate, and so on. If you don't have access to a whiteboard and you end up using a piece of paper, you do that first draft and then you cross things out in red marker pen like a teacher, and then you put things back because you erased it accidentally, and then you rename some things because naming is difficult. And if you take this to its logical conclusion, you get a mess like this. So these are admittedly some of the more extreme examples of the diagrams I see, but I still see many of the diagrams in workshops today that exhibit many of these same problems. Now, some of you might be thinking, well, hang on a second, where's UML in all of this? You know, UML is supposed to be the industry standard that we use to communicate our ideas about software architecture and design. And it's one of those things that teams threw away. I was a big fan of UML back in the late 1990s when it first came out. Probably for the first 10 years of my career, everything we did was UML based. We used Rational Rows and Select Enterprise and all these sorts of tools. But that sort of knowledge is no longer there in the industry. And I've heard literally every single excuse you can possibly imagine that teams give me for not using UML. There's a lack of knowledge out there about UML now. Yes, that's true. You tend to find there's a very small number of people on a single team who know it. And when they do admit to using UML, it's only sequence diagrams and class diagrams. I did a workshop for a very, very, very well-known company. And they said to me, to my face, during this workshop, if you use UML here, you'll be seen as old and old-fashioned, which came as a huge shock to me. The tooling sucks. Yeah, the tooling has historically been not great. It's also been very expensive, and that may have put people off. People tell me it's too detailed, and of course UML is not too detailed. It's a language. Okay, the specification is 800 pages long, and we can talk about it later if you want to, but you don't need to use all of it. But I think there's something about the UML notation that kind of puts people off, and it kind of encourages people to add too much detail when it's not really needed. People have told me it's an elaborate waste of time. It's not expected in Agile and values in the conversation, and et cetera, et cetera, et cetera. Are any of these true? Maybe partially, but actually not really. You know, a lot of these are just excuses. So what's the advice people are giving development teams these days? Well, unfortunately, it's just use a whiteboard. And a whiteboard is a great tool. So when I'm doing upfront design exercises, I will use a whiteboard because it's just a fantastic way to collaborate. It's a big space. We can erase things. It's just great for doing that sort of on-site co-located collaboration. The problem with just use a whiteboard as a piece of guidance is, well, it's not giving you any structure. It's not giving you any guidance about what the content of the diagrams should be and what sort of things you want to be showing on these diagrams. So just use a whiteboard, unfortunately, falls down. And again, I've seen this in the real world. Now, prior to the pandemic, people always used to ask me during my workshops, hang on a second, you're forcing us to use pen and paper or pen and whiteboard. What happens if you let us use a tool? And the implication there is we would do better diagrams. And of course, since the pandemic has started, I've been reverting back to online and remote workshops, and people have been using Visio, Draw.io, Miro, Mural, etc. for drawing their diagrams. And guess what? You get the same mess in a tool. Here are some examples from Google search for software architecture diagram. Yeah, these diagrams look nicer. The colors are nice. We've got nice shading. You can read the fonts. The shapes have nice rounded borders. It's all the same stuff, though. It's shapes and we don't know why, colors we don't know why, acronyms, unlabeled lines, different size boxes and we don't know why, and so on and so on and so on. So there is unfortunately huge resistance to UML, and teams don't want to use UML, and that's kind of unfortunate. And they tell me, well, we just want to use boxes and lines because that's agile and easy, in quotes. My kind of starting point of advice to these teams is this: if you are going to use boxes and lines, then make sure you do so in a structured way, and make sure you use a self-describing notation. And really, that is what this talk is all about. It's how do we put some structure into the way that people are communicating their architectures. Why is this important? If you want to be lean, if you want to be agile, if you want to move fast, if you want to deliver features quickly and iterate, you need good communication. You need everybody on the team and also outside of your team to be heading in the same direction. Now, none of this is new, right? There's literally nothing new here. If you go back to the late 1990s, Philip Crutzen created something called the 4+1 view model of software architecture. And he literally says this: to describe a software architecture, we use a model composed of multiple views or perspectives. Not many people have heard of 4+1, which again is really surprising to me. I thought it was much more well known out there. For those of you who've not seen 4+1 before, this is what it looks like. you have to kind of understand the context in which this was created, late 1990s, use cases, scenarios. Basically, you're documenting your architecturally significant scenarios from different angles. The logical view is your high-level set of logical components that somehow come together and implements your scenario. You map that to code, it's your development view. Process view talks about concurrency and parallelism, and a physical view talks about things like infrastructure and deployment. 4+1 in a nutshell. There are other ways to do this, but 4+1 is pretty common, and I like 4+1. A lot of the stuff I did in the past has been based on 4+1, and I really like that kind of multi-view angle on communicating software architecture. The thing I don't necessarily like about this in today's world, in 2022, is that we have the separation between the logical view and the development view, and I don't think that's necessary anymore. I think this has come from how we used to run our software development processes, so separate architecture phases versus a separate development phase, and maybe we had a separate architecture team and a separate development team. So this separation of process and teams is, I think, what led to this separation of the views. So why am I questioning this today? I go into organizations on a regular basis, obviously virtually now, unfortunately, and I see their architecture diagrams and they look wonderful. And then you ask the developers who are building that system, so here's your architecture diagram. Do you find it useful? Do you use this architecture diagram in your day-to-day work, in your conversations? And the answer is no, because those diagrams don't match our code. And that's the big problem here. Teams and organizations are spending lots of time and money and effort on creating these architecture diagrams, but the primary audience, which is essentially software developers, are ignoring them. And that's a problem. So one of the things I want to do here is make sure that any architecture diagrams that are created do actually map back to reality and essentially reflect the real world. This is really something that George Fairbanks in his book, Just Enough Software Architecture, calls the model code gap. Imagine you're having a discussion about architecture. During that discussion, you're going to be using words like module, component, service, microservice, subsystem, layer, and so on. These are your architectural constructs, your architectural building blocks. The languages we use, Java, C#, Ruby, etc., they do not contain those same architectural building blocks as first-class programming level constructs. So imagine you're building a Java application and you consider it to be a bunch of components organized into layers. Well, the Java language does not have a component keyword. It does not have a layer keyword. So how are we creating these architectures? Well, naming conventions, packaging conventions, module conventions, et cetera, et cetera. There's lots of ways to do this. And the model code gap is essentially when your top-down view of your system does not quite match up what the code looks like. How do we fix this? I think we need to go back and I think we need to figure out what is the common set of words we want to use to describe the architectural building blocks. And I don't think we have that today, or certainly in widespread use. And this sounds like a really weird thing to say in 2022, because sure, teams are using words like module and component, and surely they know what they mean. But no, I've been in meetings with teams and people have been using these words and they've been completely talking about different levels of abstraction in their code base. We don't have this problem in other disciplines or domains. So this is a map of London. And you can see running through the middle of this map of London is the River Thames. And we all know what a river is. It's a moving, flowing body of water. This map has a one-to-one mapping with the real world. We can walk outside, we can go find more rivers. This thing here is a top-down floor plan of a bathroom. And again, there's a one-to-one mapping here between this and the bathroom that was ultimately created. Circuit diagram, same thing. You can have a bunch of different ways to describe electrical circuits. So if you look at the bottom diagram, you got that little zigzag, that means a resistor. And you could go find a resistor. And again, there's a one-to-one mapping with something in the real world. When it comes to software, we draw stuff like this. This is a UML component diagram that I stole from Wikipedia. And it's a really, really poor example of a UML component diagram. All of these boxes should be components. I mean, that's the whole point of the diagram, of course, but they're all very different. Some of these components around the outside particularly are stereotyped COTS, which I think is commercial off the shelf. You've got a document management component, and identity management component, and a rules engine. So those sound like vendor products that we install. And then we've got that big component with smaller components inside it. Are they smaller components or subcomponents? Or is the big thing a super component? I have no idea. We've got UIs and engines and servers and all sorts of stuff going on there. And I have no idea what this system is. Is it a Java app? Is it a C#.NET app? Is it a set of services? Is it a monolith? Who knows? And this is the problem. I want a set of diagrams that make sense inherently to software developers because that's the primary audience. So yeah, words like component, they're just too overloaded. It just means part of something bigger. So my overall tip here is when you're drawing software architecture diagrams, you should think like a software developer. And the reason I say this is because when I run my architecture katas and I see teams do designs, I'm confident that 99% of all of the designs I see are implementable, they're feasible, and they're going to work. The problem comes when you ask the teams to visualize and draw those solutions. They seem to forget everything they've ever known about software development. They put their architect's hat on and they say, right, how would an architect draw this solution? And they come up with all of these weird abstractions that just don't exist in the code base, and they start kind of making stuff up. Here's a drawing of my house, viewed through the eyes of a software developer. I mean, this is completely useless. I've just made up a whole bunch of random abstractions here, and I've got horizontal layers and vertical layers for things like cross-cutting concerns. So it looks like I've got water in my living room, which I hopefully haven't at the moment. If you asked a building architect or a structural engineer to draw you a diagram of a house, you wouldn't get this garbage. You'd get blueprints and floor plans and cross sections, elevations, and something that maps to the real world. So how do we solve this? Because there's not much appetite for using UML, and of course UML does give you a common set of abstractions and a common set of boxes and lines notations to represent those abstractions. Maybe that's too much for software developers these days. So maybe we need to instead focus on what are we trying to show here? What are the abstractions that we really want to think about to describe our software architecture? And that's why I say this. I think a common set of abstractions is actually much more useful than a common notation. Now, of course, if you think back to the electrical circuit diagram, when you draw that zigzag, we all know what that zigzag means. And I actually think that's a really good point to get to in the software industry. So when we draw a box, we know exactly what that thing represents. But I don't think we're there yet. I think we need to do some more work. So yeah, a common set of abstractions, I think, is more important than a common notation. And this sounds like a backward step. I completely admit that. But there's a really good real-world example of this, and it's a map. If you take two maps of your local area and you put them side by side, the two maps are going to show you the same things. The city centre, the shopping mall, the rivers, the forests, the schools, the churches, the bus stations, the train stations, the metro routes, and so on. The two maps will show you the same things, the same abstractions, but they'll likely look very different. Different color codings, different shadings, different icons, different symbols. How do we decipher maps? Well, there's a key in the corner. There's a key or legend in the corner, and it says, when you see the symbol, it means X. And that's really powerful. So I consider a map, a real world map, to be a self-describing diagram. It's a well-known set of abstractions with a self-describing, well-contained, self-contained notation. And that's really the thing that I'm going to steal here. So what are the abstractions? When I'm thinking about describing and documenting and diagramming something, I'm going to start with the biggest abstraction, which for me is a software system. This is the hardest one of these abstractions to clearly define. When I say software system, what I'm really referring to here is something a single team is responsible for, something a single team owns, something a single team is building, something a single team can see the entire implementation details of. That gets a bit complicated when you start thinking about service-based architectures, but if you're doing the kind of Amazon Netflix thing and you've got a whole bunch of different teams all owning their own individual services, then maybe the service is a software system. Once you look inside these things I'm calling software systems, I'm going to say they are made up of containers. Now, I'm not talking about Docker. apologies, there's an unfortunate clash of naming here. I came up with the name first, but that's completely irrelevant because Docker is way more popular. By container, I'm basically referring to an application or a data store. So something that runs your code or stores your data. In real world terms, a container is something like an AngularJS app running in a web browser, a React app running in a web browser, could be a mobile app running on a mobile device, could be a server-side web app like a Spring Boot app, Spring MVC app, ASP.NET MVC app, Ruby on Rails app, could be a console app, could be a C# Windows service. From a data perspective, a container could be something like a database schema, could be a folder on a network share, or it could be something like an Amazon S3 bucket. So a container is an application or a data store. It's the high-level technology choices that make up your software system. Most containers are generally, but not always, they're generally individually deployable units. They're separately deployable units. Look inside the containers, specifically the code-focused containers, and I'm going to say they contain components. This is where the terminology and the naming comes from. So containers contain components. So yeah, I just said that component is an overloaded term. I do want to use the word component, and I want it to mean a grouping functionality, hopefully a nice, well-defined, clean interface running inside a container. So the big difference here from other ways of thinking about components is that in this approach, components are not separately deployable artifacts. It's the container that's the deployable thing, and components run inside containers. So we've got some hierarchy there. Open up the components, and they're basically made of code. So if you are building a Java component, your Java component is made up of classes, interfaces, enums. Same with C#, same with C++. If you're using JavaScript, then it's objects and functions. If you're using F# or Haskell, it's functions. So really that bottom level represents the code level constructs that you have in the languages that you are using. And that's it. A software system is made of one or more containers. Containers contain components. Components are built from code. So it's 4 levels of abstractions that are by nature hierarchical. And now, half an hour in to the talk, we can finally get to the topic of the talk, which is the C4 model for visualizing software architecture. C4 stands for context, so system context, containers, components, and code. So it's, again, 4 levels of diagrams. The diagrams are hierarchical, and they map onto the 4 levels that I just went through in terms of abstractions. And it's literally a zoom in movement. So you draw your system context diagram. Your system context diagram shows you systems and people. You choose a software system box. You zoom into it. You look at containers. You zoom into a container. You look at components. You zoom into a component. You look at code. The concept here is diagrams as maps to kind of bring the maps thing back into this. So I live in Jersey in the Channel Islands, which is a tiny island off the coast of France. If you open up Google Maps and you do a search for Jersey, you'll likely get the third image where Jersey kind of fills the screen. That's a great image if you want to know where the major places are, where the major roads are, if you want to know where the airport is. If you've never heard of Jersey, it's too much detail too quickly. How do you fix this problem? How do you get more context? Well, you zoom out, you pinch to zoom out. And then if you zoom out a little bit, you can see it's off the coast of France. If you zoom out and zoom out and zoom out, it disappears because it's a tiny island. If you zoom in more and more and more, you eventually drop into something like Google Street View. And that is a nice one-to-one mapping of reality, of course, when the photographs were taken. And the software architecture diagrams, the C4 diagrams, are kind of the same thing. We want different levels of diagrams at different levels of zoom, at different levels of detail, at different levels of abstraction that allow us to tell different stories to different audiences. That's the thing I'm going for here. The other way to think about this is the diagrams are essentially a set of maps that help software developers navigate large and complicated code bases. To give you a quick example, you can find these examples on the C4model.com website, and you can zoom in and click around and stuff. So this is an example system context diagram for an internet banking system. So imagine we work for a bank and we've been asked to build an internet banking system. This diagram is basically showing you the internet banking system. That's the blue box in the middle. It's showing you, in this case, the one type of user who is using this system. In this case, it's a personal banking customer. And they are using the system to view their account balances and make payments. This system is in turn making use of a mainframe banking system that sits inside the bank. That's where all of the core banking data is being stored. And the internet banking system is also making use of an existing email system to send emails to our customers. So the system context diagram is essentially showing you two things: people and software systems. By people, I mean users, actors, roles, personas, however you want to think about people. And software systems are essentially your other external dependencies, things that you are using or things that are using you. So that's the context diagram. Now we can do the pinch to zoom movement, and essentially what we do is we pinch to zoom on that internet banking system box, and we look inside it, and we start to now identify the containers that sit inside that system boundary. And this is an example container diagram. One of the things you'll notice is that you end up repeating elements across the different levels of the diagrams. So the context diagram showed you the personal banking customer, the email system, and the mainframe banking system. The container diagram shows you those same elements because they're part of the same story. And what we've done here is we've kind of opened up the software system box representing the internet banking system, and now we're showing the containers inside it. And this is an example design for an internet banking system. So let me just quickly walk you through it. Imagine you're a customer of the bank, you're sitting at your computer, you open up your web browser, you go to bigbank.com/IB, you hit enter. I'm going to say that request is serviced, it's processed by a web application, server-side web application. In this case, I'm saying it's a Java and Spring MVC web application. And all that thing is doing is it's delivering static content back to your web browser. By static content, I mean HTML, CSS, and JavaScript. Once that static content comes back into your web browser, I'm going to say, right, what you essentially have now running in your web browser is a single page application. It's a JavaScript and Angular app, and that's going to be your browser-based UI. Let's also give our customers a mobile app. So because we want to target different devices, we're going to use the Xamarin framework for cross-platform development. We've got an API application sitting at the bottom there. So our two UIs are going to make JSON over HTTPS API calls to an API application, which we're going to build. That's going to be another server-side, separately deployed Java and Spring MVC application. And that's going to make calls to the existing mainframe banking system over some proprietary XML over HTTPS interface. Finally, we have a database sitting there on the left-hand side. The bank uses Oracle, so this is an Oracle database schema, and that's where we're going to store internet banking specific stuff. So really that's my container diagram. It's showing you the high-level building blocks. It's showing you how we've decomposed the responsibilities across those high-level building blocks. It's showing us the technology choices of those high-level building blocks. And it's also showing us the typically inter-process communication, so the intent and also the technologies and protocols involved there. So this is a really nice diagram from a developer perspective. It's like, this is all the stuff we're building, and this is how it kind of fits in and works together at runtime. I should note that this diagram doesn't actually tell you a whole bunch of other things that are useful. Clustering, failover, all of the infrastructure stuff, deployment stuff, etc., etc. All of those things are super useful, but I want to save those for a separate diagram to avoid cluttering this one. So that's my container diagram. To continue the story, we can now choose an API application, a container in this case, and we can zoom inside it and we can show the components. And again, we're repeating elements from the previous diagram. In this case, the two UIs, the single page app and the mobile app, the database, the email system, and the mainframe banking system. And what we're seeing here is really the components that sit inside that API application. At level 3, the goal here is to show the high-level constructs that exist in the code. So if we were to build this system for real, and we were to open up the code for the API application in our IDEs, I would expect us to be able to find these 6 things very, very clearly and very, very quickly. And that's kind of reiterating what I said before. I want architecture diagrams to reflect the real world. And that's why I want to show the high-level code constructs in my component diagram. If you're building an application and you consider it to be made up of components and layers, this diagram shows you components in layers. If you're using a hexagonal architecture, ports and adapters, clean architecture, package by feature, your component diagram essentially shows that structure. So again, we want these things to reflect reality, and we can now start to weave in some of those lower level technology choices, maybe some of the low level frameworks that we're using here. To continue the story to conclusion, we can take, in this case, the mainframe banking system facade, which is a horrible name. We can take that component and zoom inside it, and we get down to level 4, which is the code level. And it turns out this is where UML is actually super useful, especially if you're using an OO language. In this case, this is a kind of hand-drawn diagram, just presenting a summary of the classes and interfaces that sit inside that component. Once you get down to level 4, I definitely recommend automatic generation of these things. This is relatively trivial with most IDEs. So if you've packaged your code well, in your IDEs, you can often just right-click a folder or right-click a package or something and say, generate me a class diagram from everything in this package, and it will give you something like this. You might need to turn off things like attributes and methods, but that's relatively straightforward to do. Just a quick caveat about the C4 model. Although it has the number 4 in the name, I don't necessarily recommend doing all 4 levels. That's not the intent of this. It's just a set of diagrams at different levels of abstraction. Most of the organizations I worked with around the world, when they adopt the C4 model, they get the most value from levels 1, the system context diagram, and level 2, the container diagram. I've seen a few drop down to level 3 components, and I've seen hardly anybody do level 4. Level 4, as I said, automatic generation is key here. If you want to go down to level 3, particularly if you are describing an existing code base, then again, you want to really look at automatic generation of those component level diagrams. That's not trivial because of this model code gap. Going back to 4+1, what I've really gone through so far are really just the static structural diagrams. So all of the C4 model diagrams represent static structure, albeit at different levels of the hierarchy. And that's not enough in many cases. So if you go to c4model.com, there's also a bunch of supplementary diagrams that are listed on the site. The first of these is a system landscape diagram. And really, this is just a system context diagram, but showing more systems and more people. So what I've seen many of my clients do is they have a single system landscape diagram, maybe one per group or one per department, or maybe one for the whole organization if it's a small organization. And then they have a C4 model drill down for each system that they want to describe. So really the system landscape diagram is a map of the system, sometimes overlaid with system ownership, data ownership, that sort of thing. The second supplementary diagram is what I call a dynamic diagram, and it's essentially a UML collaboration diagram, but reusing the existing notations and stuff that we've seen. So the C4 model dynamic diagram is essentially showing you static elements from the various levels of the previous diagrams and how they interact at runtime. It's an ordered set of interactions in a free format manner. The other way to do this, of course, is to draw a regular UML sequence diagram. And the third supplementary diagram is a deployment diagram. Again, UML has a deployment diagram. What I'm trying to do here is just slightly simplify it, and I'm trying to say this deployment diagram is showing you the mapping of container instances, or maybe software system instances, onto things that exist in the infrastructure world. I just call those things deployment nodes or infrastructure nodes, and you can find more information about those online. I'm actually going to show you an example deployment diagram later anyway. Some of you might be thinking, well, you've got blue boxes and gray boxes and people, and you said that we should have a diagram key, and you never showed us a diagram key, and what's your notation? One of the things that people kind of get wrong with the C4 model is they tell me that the blue boxes and the gray boxes is the C4 model notation, and that's not the case. So there is no C4 model notation. It doesn't exist. The C4 model is basically two things. It's a set of abstractions and a set of diagram types. That's it. You can therefore use any notation that you like. You can use boxes and lines of different colors. You can use different shapes. You could use UML or Archimate as well. So I have seen a small number of teams using things like UML stereotyping. They've created their own UML profiles, and they're basically applying UML, but they're using the C4 model abstractions and diagram types. And of course, that's absolutely fine. That's a nice way to join these two things together. If you want to go down the boxes and arrows route, you should definitely think about your notations. Let me give you a quick few notation tips here. If we forget level 4 for a second, the the context, container, and component diagrams essentially only show these types of elements. So the context diagram will only show people and software systems. The container diagram will show people, software systems, and containers. And the component diagram potentially shows people, software systems, containers, and components. I'm going to give every element on the diagram a name. Hopefully it's a good, well-intended name, but we all know name is hard. I'm also going to be very explicit about the type of this element. Is it a person that we're showing? Is it a software system? Is it a container? Is it a component? So I want that text to be very clear on the diagram inside the element. Because containers and components are more technical in nature, well, that's where we can start weaving in the technology choices if we have them, of course. The rest of the text in the box is really just a short description. Like you see here, it might be a single sentence describing the major features of that element, or maybe it's a short set of bullet points, so maybe like 5 or 7 bullet points detailing the key functions or features of that thing. And it's at this point people say, Simon, why are you putting so much text on your diagrams? This is not how we draw diagrams. And that's exactly the problem. The diagram on the left here is very typical of a software architecture diagram. It's just a bunch of named boxes. If you see that diagram for the first time and I ask you, what do you think the file system does? The only answer you can possibly give me is, well, it stores files. There's not enough information on this diagram. It's just ambiguous, it's vague, and the naming is just horrible. So again, I'm adding more text. If you look at the difference between the diagram on the left and the diagram on the right, I'm adding that text. I'm adding the text about the types of the elements, the technology choices, and the key responsibilities. So now we can look at the file system box, and granted, it's a silly name, it's a horrible name, it doesn't really make sense, it should be better named. But now we can see that, oh, that thing stores search indexes. So that gives us a nice at-a-glance view of what's going on here. Lines. One of the big questions I get all the time is lines. How do we draw lines? Which way do arrows go, etc., etc.? My preference is that all lines on a software architecture diagram should represent one-way arrows, so unidirectional relationships. That raises the question, which way do you point them? It's up to you. There's no right answer here. If you take any pair of elements on any diagram, there's normally a request response pair between them. So in this case, the single page application makes an API request to the API application, and the API application is sending a response back. It's a request response pair. There's a bidirectional relationship here. This is true, this is accurate, but if you start adding every pair of relationships between every pair of elements, you get a very complicated diagram. So what I tend to do instead is I'll summarize the intent, I'll collapse that bidirectional pair into a single unidirectional arrow. So in this case, I'm going to say that the single page application makes API calls using the API application with an implicit, let's hopefully get an answer back. Having said that, there are times when you do want to show both directions. So imagine we have a microservices architecture. Maybe when service A starts up, it has no state, it's stateless, and it will ask for a list of customers from microservice B. And maybe that's asynchronous, I would like an answer now, please. And it's a JSON over HTTPS API call. At runtime, maybe microservice B is broadcasting new customers over a Kafka topic to which microservice A is subscribed to. So in this case, it does make sense to show both arrows because they're showing different relationships with different intents. One is synchronous, one is asynchronous, and they're using different technology. So that's a really good example of where you might want to show both directions. When you get into describing things like service-based architectures and specifically message or event-driven architectures, it's very tempting to draw diagrams like this. It's your traditional classic hub and spoke architecture. So here we have microservices architecture, A, B, C, and D. Services A and B are throwing stuff into Kafka, and C and D are somehow subscribed to those things coming out the other side. Again, this is true, this is accurate from a perspective, but it might be hiding the true story. Maybe, in this case, the true story is actually this. Maybe microservice A has a coupling to service C, but those messages are going via Kafka. And maybe B is coupled to D, and that's going by a different Kafka topic. So that's one of the other ways to think about this. What's the story that we're trying to tell, and how do we best tell it? To come back to that whole question about arrow direction, you'll notice on this diagram that all of the arrows are going from the left to the right, and they say things like sends customer update messages to the thing they're pointing to. It's very possible to flip most arrows and change the text, and the thing still makes sense. So if you look very carefully, what I'm going to do now is I'm going to flip the direction of that right-hand arrow. So 3, 2, 1. So now we're saying that microservice C is subscribing to customer update messages from Kafka topic X. So we flip the arrow, we've changed the text, and that still makes sense. And that's another way to describe the same thing. Which one's right? This version or the version I just showed you? They're both correct. They're just different ways. You know, everybody has their own preference on doing this. One of the other things you might think now is, well, hang on a second, that topic box is just noise. It's not really adding much value. And you're exactly right. So maybe we can just remove the topic box entirely. And now we're linking up A and C, and we're just saying sends customer update messages to via Kafka topic X. So this is a slightly more implicit way of describing the same thing. It's less cluttered. Again, it's all trade-offs. You choose the one that you like the best. Keys and legends, whatever notation you use, and actually, even if you are using UML or Archimate, I still recommend using a diagram key or legend, because chances are most people won't understand the majority of the notation that you're using. So make sure your key or your legend explains your shapes and your line styles and your colors and your borders and all of that stuff, even if it seems super obvious to you. What might that look like? Here is my internet banking system container diagram, and this is the key or the legends that I use to describe it. The white box for the dashboarder, that's the internet banking system. Lighter blue boxes for containers. I'm using different shapes for different types of containers. We just have a single type of person here. The gray boxes here are existing systems, and I'm just saying that we have relationships. I'm not being specific about the types of relationships, but you could do. You could use solid for synchronous, dashed for asynchronous, green for secure, red for insecure. You could have a dashed green line representing a secure asynchronous. Just make sure all of that stuff is included on your diagram key as well. People ask me about arrowheads. I would steer clear of arrowheads because it's a very subtle notation. If you've got a big diagram and you zoomed out, I think a lot of people miss arrowheads. So just be careful. By all means, do so. But if you're using boxes and lines notation, I would steer clear. If you're using UML and Archimates, then you should definitely use the arrowheads provided by the notation. So yeah, use shape, use color, use size to complement a diagram. That already makes sense, but don't use things like color to portray lots of primary information. Because of two things really, black and white printers and things like red-green color blindness, that's actually quite predominant. One of the reasons we want to use shapes and color is because it makes the diagrams look nice. That's a big part of this. If your diagrams look nice, they're going to draw your readers in. And also it gives the elements a bit more visual distance. Here are two example diagrams. The one on the left is just all boxes. It's a bit boring. The one on the right has a few shapes thrown in. You can look at the diagram on the right and you can start to make assumptions about, oh, I know where my users are expected to be now. Fundamentally, the diagrams have the same information that's in the text, which you probably can't read, but the shapes add a certain degree of extra information to the diagrams, which is nice. All of the advice I've just given is also applicable to icons. Why? Because I see everybody doing this these days. It's those horrible AWS and Azure and Google Cloud architecture diagrams. They download the icon sets for Visio and they just knock themselves out. And these things are horrible. I have no idea what half these icons mean. Every time Amazon runs a conference, they invent a whole new bunch of services, and therefore you get a whole new bunch of icons. This is just not a good software architecture diagram. It might be great to showcase the features you are using in AWS, but it's not a particularly good architecture diagram. So don't rely on icons, is essentially what I'm saying here. Do use icons if you want to. So here's an alternative version of my container diagram. We've taken off the blue, and now we're using different icons to represent different technology choices. If you know what these icons mean, you can say, great, there are two Java Spring apps, an Angular app, a Xamarin app, and an Oracle database. If you don't know what the icons mean, well, guess what? They're included in the key and the legend. The reason I bring icons up, of course, is, as I said, it's the AWS side of things. I see lots of people drawing diagrams like this. So this is describing something running in Amazon Web Services in US East 1, Route 53, Elastic Load Balancer, EC2 running in an auto scaling group, and RDS with MySQL. Again, this tells you something about AWS. It doesn't tell you anything about your software system. So what I recommend teams do is they think about how do we apply the C4 model to things like deployment diagrams. And this is how I would redraw that diagram. I'm still going to use the icons, I'm still going to use the colors, I'm still going to use Route 53 and Elastic Load Balance and so on, but I want to show where instances of these containers are deployed onto the Amazon infrastructure. So that's really how I kind of blend all these approaches together. So again, we're using icons here to supplement the text, not replace it. And my whole goal here, just to wrap up, is I want these diagrams to stand on their own. I appreciate we don't create diagrams to be stood on their own, but what happens is people take your diagrams, they copy paste them out of Confluence, they stick them in an email, they send them around to a bunch of people, and the narrative is lost. If people have to ask, what does the red box mean? What does the blue box mean? There's a level of misunderstanding that's going to happen. So I want the diagrams to make sense through things like the diagram keys and legend. Any narrative you give, whether that's documentation or whether it's a verbal presentation, should complement the story that you're trying to tell. Your narrative should not explain things like notation. It should be telling stories on top of the diagram. How did we do this? Why did we do this? And so on. If you want to draw better diagrams, if you go to the URL behind that QR code, which takes you to c4model.com/review, there's a quick one-page diagram review checklist. Go through this very quickly, click yes or no, and it will hopefully give some hints and tips on how you can better improve your notation. So, last slide. The whole purpose of this talk is to talk about the C4 model. The concept behind C4 model is essentially abstractions first, notation second. Software systems, containers, components, and code, that's the small set of abstractions. We have the 4 diagrams, the context diagram, container diagram, component diagram, and code level diagram. And once teams agree upon these abstractions, they can have a varying or variable notation. And I've seen this work really well in the real world. So make sure your team has ubiquitous language. This doesn't need to be a ubiquitous visual language, but you should at least agree upon the abstractions that you want to use to describe your systems. So that's me. Thank you very much. Do we have any questions, I guess?
Or host video turning on and whatever. Is there, do we have like an urban dictionary definition, word to use for getting prepared for a video or a video interaction? I mean, it feels like it needs to be called like a shallaloquy or something. You know, I've got to get my shallaloquy done, and then I'll be able to join you. I think the top question we have, first, we have a couple of comments. Great presentation. A lot of people had that to say. Obviously, a very polished one as well, and about a very specific topic that I'm passionate about, which is design skills, and not design skills like, oh yeah, I know what a singleton pattern is, but the design skills are a whole host of very difficult, or not difficult, but things you have to practice and things you have to be specific on. In as much as, you know, I may code in .NET or I may code in Java, and to switch between the two, I still have a lot to learn, regardless of how many years I've been programming. And design skills, I think this is one of them. So one question about arrow direction. Agreed, it's all about which story you want to tell and in what details. So it depends, but what do you think about the general categorization, like showing the direction of information flow, or show who acts and who is acted upon, basically the verb, a noun, or, you know, package and content, etc.?
Yeah, it's a really good question, and it's something we end up discussing for quite some time during my workshops. So my preference and the way that I do this, because this is just the way I think about the world, is that I tend to show the initiator with an arrow to the receiver. So because I've done lots of UML stuff in the past, and I tended to like things like dependency relationships and users type relationships, I generally say like thing A depends on thing B, or thing A sends stuff to thing B. I have met many organizations who prefer data flow and message flow and event flow, and of course that's absolutely fine. So this is one of the things I basically say, it's entirely up to you. My preference is the dependency style relationships, but other teams will have their own preferences, and that's fine. As long as the arrows are labeled, they should be understandable, hopefully.
So again, going back to design systems, and we got Grady on, who obviously helped to invent UML and many of the design systems languages. So it kind of a really interesting overlap there in that you showed. I was really happy that you showed. You didn't get into views and viewpoints much. You've mentioned it tangentially. So if I want to use C4 to understand or to understand an infrastructure view versus a software, let's say we'll just go with the generic term software as opposed to say performance and things. How do I think about the abstractions in relation to those? Do we use those terms synonymously in the sense of something contains something? Or where do I land with these different views?
So I only went through this kind of briefly. So the C4 model diagrams are really static structure focused on the software side of things. And for most systems that I document myself, I will also describe something about the deployment and infrastructure. So if you look at the C4 model website, there are two concepts that are present on deployment diagrams. So it's deployment nodes and infrastructure nodes. An infrastructure node is just something like a router, a load balancer. It's just a thing that is being used. And a deployment node is anything from a physical server, a virtualized server, a Docker container, a web application server, could be a data center, could be a physical server. So those deployment nodes are really anything that exists in the infrastructure world, and they can have some degree of nesting. So that's what I want to show here. And ultimately, when you drill into deployment nodes, you end up with instances of the C4 model static structure containers running somewhere on that hierarchy of deployment nodes. So that's kind of where I bring the 4+1 stuff back into this. I do want to look at my system from a deployment angle in many cases, and of course you might have a bunch of different deployment diagrams, one for your dev environment, one for your staging environment, QA environment, test environment, live environment, and so on. So it's definitely useful. Does that answer your question, or did I just answer a completely different question? Did I interpret it wrong?
I think a little bit of both. I mean, being, I think not really. I mean, I don't think there is a conclusive answer to my question right now, right? In the sense that we have viewpoint libraries that work together to give us large concerns and perspectives. We have modeling notations, and we have definitional concepts and decision records that help us trade off. And a lot of those things relate to each other at a very fundamental level. As we get into like principles and guardrails and axiomatic, building codes. The physical world contains a lot of very human-based identifiable objects. But the world we live in contains a lot of made up representations of conceptual linkages. So we do have a specific question. We'll make last one. What are your thoughts on showing flow, source, destination, and consumer perspective, top to bottom flowing diagram? Flow. I'm trying to think of where that might source and destination. I'm thinking about that as kind of activity methods, things like what in 4+1 or UML would be kind of an activity diagram, but I'm not positive if Paul, that's what you mean. Paul LaRue asked the question.
So if it's how do I show things like business processes and workflows, I would probably just use a UML activity diagram. That's generally how I do things. So one of the things I should say, and I didn't say this in talk, is don't go and throw away all the other diagram types out there. So if you do need to show business processes, UML activity diagrams, if you're building a state machine, use a UML state chart. There's a whole bunch of other diagrams in Archimate, SysML, BPML, you've got data flow diagrams. So there's a whole world out there of other diagrams that teams can use to supplement the diagrams that I've been through to describe their software from different angles. So that's something, we need to have all these things in our toolbox essentially.